Hello everyone, I'm getting ready to derive the formula for the moment of inertia of a cylinder. This is actually, instead of a cylindrical disc, it's actually a full-size cylinder with a thickness T, radius R, and a mass M, and the mass is uniformly distributed. I'm going to derive it using an integral formula, and in addition to using the integral formula, I'm also going to do it with a single integral as opposed to a double or triple integral. I will be doing double and triple integrals later, just to show you how those are done. And also it helps for more advanced classes, but it also helps you better understand how to do multiple integrals. So let's get started by sharing my iPad screen. So I've got the problem written up. It says a cylinder has a thickness T, a radius R. Actually, that should be a radius R, not a radius is R. You'd think I would have caught that beforehand. And its mass M is uniformly distributed throughout the cylinder. Use integration to calculate its moment of inertia when rotated about an axis perpendicular to the disk and through its center. So we're going to do that, and I'm going to do so by single integrals. I'll start off with writing solution. And what we know and what we need to use is that I is equal to the integral of r squared dm. And when you use such an integral, the formula requires that we're sort of treating the r squared as the integrand. So when you actually do something like that, you got to make sure your dm, which is a differential in the integral, that dm cannot differ in value of r by more than an infinitesimal amount. So for instance, if you had a macroscopically different r from one edge of the dm to another edge of the dm, then you'd actually have to do some other process to find out what the best representative R is for that, like an averaging process. So you just want to make sure you choose your DMs appropriately. Uh, Generally speaking, our DMs are either DM is equal to lambda times DL for one-dimensional objects, or sigma times dA, a differential area, and this is for two-dimensional objects, and rho dV, which is the volume integral, and of course that's the for three-dimensional objects, which we will do later, but right now we're sort of treating this to some extent like well, yeah, I guess we are to some extent treating it like a row. So I'm going to actually be doing it in three dimensions right now, this one. So we also know that the cylinder has a mass M, it has a radius R, and it has a thickness T, and we know it's uniform. And uniformly distributed mass means one of those densities that I wrote above, the lambda, the sigma, or the rho, is a constant. In this case, it's three-dimensional, so let's say rho equals a constant. Now, to get this started, it's helpful to have a coordinate system, so I'm going to try to draw a coordinate system that would be convenient for us. That looks pretty good right there. This looks pretty good there as well. I'm going to say this is my x-axis and this is my y-axis. And now I'm going to draw the cylinder in space. And what I'm going to try to do is I'm going to try to get it to draw a really good, basically a really good ellipse to represent the actual cylinder. It would actually look, of course, like a circle, but we're attempting to look at it in three dimensions, and that's going to force it, of course, to have a slightly different shape that makes it look less than circular or different from circular. So here I am trying to compel my program to write this appropriately, and that looks like it did pretty good. The only thing I'd say is that dot needs to be erased, and I was planning actually on extending the little end here because I wanted to actually make that ellipse a little more appropriate. It's actually sort of tilted, but that's okay. We'll just leave it as is. Now I'm going to connect that down to the base of the cylinder, which of course will also be in the XYZ plane. And to do that, I'm again going to try to draw it as neatly as possible. So I'm trying to run it into here and here. And again, I'm going to try to make an oval as best I can. That doesn't look great, but it's not horrible either. So I'll put it like that. Of course, we're not supposed to be seeing that back edge back there. So in principle, this line back here should be dashed. So I'll do it like this. And that should be good enough. So what we're saying in this diagram is that the radius is in fact R, that the mass is M, that the thickness is T, and that the density, which is actually a volume density, rho, which would be dm dv, reduces to mass over volume, which for this case, we see the mass is just going to be m, and the volume is going to be pi r squared times t. And the fact that it's uniform allows us to use that formula m over pi r squared t, and the fact that it's uniformly distributed means that is, of course, a constant. So we're going to make use of that, and now we're going to begin by choosing a differential volume element. So again, the formula that we use is the integral I is equal to the integral of r squared dm. And like I said, when you make a dm, you have to make sure that the integrand does not vary by a macroscopic amount at any from any part to another part within the DM by a macroscopic amount. So, for instance, if I were to say this is going to be my differential area element or differential volume element, if I wanted to say draw it in 3 dimensions, then the fact that the R differs by quite a macroscopic amount from this end to this end means that I shouldn't be using that as a differential. If I use that as a differential mass element, then I'd have to figure out some average R to use for the R squared value there. So now I'm going to erase that, and what we're going to use is something like we did before. Specifically, we're going to imagine that there's a little stripe on top that is basically the top of a cylinder minus the top of a smaller cylinder. And of course, it's going to have sides and stuff like that. But we're going to do it the same way we did basically with the thin disc. So what I'm going to do is attempt to draw a differential volume element, and that differential volume element is going to go from here to here, and then it's going to be back to roughly here. So I'm going to attempt to draw it with the computer program automatically making it neater for me. And hopefully that'll work. That turned out pretty well. Now, in addition to that, I'm going to try to draw another one just outside of that. So I'm going to keep it sort of narrow in front and back, but about the same thickness on the edge. Sorry, it automatically jumped into that other idea. So what I'm going to do is do it around like this, very, very thin, a little wider, very, very thin, little wider, very, very thin like that. So that is the top of my differential volume element. My differential volume element is actually going to extend down though to the bottom surface as well, so that we'll see something on the order of or something like this. I'm going to say like that. And again, that's the outer one. So now I'm going to draw the inner one like so. And then you can also see that this dotted line comes down to here and comes down to here. Now, what this really is a cylinder, a big cylinder whose radius is r plus dr, and then you subtract from it a small cylinder whose radius is just plain r, and that's actually what the differential volume element is. But we can treat it like this, as we did in calculus. Basically, we're going to treat it like it's a rectangle. Like if I cut that thing open, basically it would be a rectangular solid that would look something like this. You could imagine. I'll do it in red. You can imagine it would look like this. That's supposed to be roughly there. This is there. And I'm not foreshortening them. That's not why those sides are actually angled like they are up here. They're not actually, uh, it's not me showing perspective and depth and that sort of stuff. It's the fact that the inner one is actually, the inner surface is actually a shorter length rectangle than the outer one. For instance, this goes like that, this goes like that, and this goes like that. If it wasn't for this little triangular ends right here and here that go all the way down, of course, if it wasn't for those, it would be a rectangular solid. And we would say that this thickness from here to here would be just dr. And then this, of course, would be t. And then this inner one would be 2 pi r, like that. Should show it there. So that's really what the shape is. And in fact, this length down here is actually 2 pi times r plus dr. So that's where the a little triangular end cap comes from, because it should technically be, if it was a rectangle, it would be basically straight back like this and straight back like this, so that both of them would have a length of 2 pi r instead of 2 pi parentheses r plus dr. So that's really what the shape is. We're going to basically imagine that because of its infinitesimal size, those little triangular end caps on the left and right end are negligible, and they are. They're actually going to be on the order of dr squared or larger. So with this in mind, I'm going to say that this dm right here is equal to rho times dv. We've already calculated what rho is, but dv we're going to say is approximately equal to, I'm again going to say 2 pi r, that's the circumference of the inner circle. If I multiply that by dr, that sort of represents the top other than those little triangular caps. So I can say 2 pi r dr. But I also now, since it's a volume, I need units of cubic meters instead of square meters. So it's also going to be times the thickness T. So that's really what it is. In reality, though, if we actually worked all the details, what would require to be would be dV is actually equal to pi times r plus dr squared times t. So that's the bigger outer cylinder. Uh, Minus, I need the smaller inner cylinder, which is pi r squared t. So if you actually computed that, what you get is pi times t is common to both terms, but I also got r squared plus 2r dr plus dr squared minus r squared. And you can see, of course, that the r squared cancels out with this r squared, and then this gives you the 2 pi r t times dr. This is on the order of dr squared, so we can ignore it, because if dr is infinitesimal, then dr squared and dr cubed and dr to the fourth power should always be even smaller infinitesimal. So now we'll just go on with that. We're going to say the integral is r, and we're using the variable r, so that's no problem. It's going to be r squared times rho times 2 pi r dr times t. Now I'm going to pull out all of those constants, which become 2 times pi times rho times t, integral from r equals 0 to big R of, now we have r cubed dr. Now that we have r cubed dr, that's a trivial integral. The integral is just 1/4 r to the fourth. So I'm going to get 2 pi t over 4. I'm putting the rows separate because I'm getting ready to substitute that in. And then 1/4 r to the fourth becomes 1/4, which I've already got the 4 out there, and then times big R to the fourth. So that's what that is. We can automatically cancel out this and replace it with a 2 and replace that with a 1. But now I'm going to go ahead and substitute in what for what row is. So now I have pi t r to the fourth over 2 times, now my row is m over pi r squared t. Now you can see that the t cancels out with the t. The r to the fourth cancels out all of the r squared, leaving an exponent of 2 in the numerator, and the pi is canceled out by the pi. So I'm finally left with exactly the same formula I got for the disk, and that is the moment of inertia for a cylinder about its center of mass is equal to 1/2 mr squared. And that's it. That's straightforward enough, and I did quite a bit more detail than would normally be allowed in a physics class. So hopefully that helps you. I'm going to go ahead and call it. Have a good day. Bye bye.